Okay, so today we're going to start talking about gas laws. So this is all about gases and how we figure out things like their pressure and their volume and all of that. So starting out, talking about pressure. And basically, all the pressure is a measurement of the amount of force over a given area, right? So force divided by area gives you pressure. There are several units here that we define pressure by. One is the Pascal. This is the standard unit for pressure, standard scientific unit. There's also bar, which is related to pascals by the fact that 1 bar equals 10 to the 5th pascals. Atmospheric pressure at sea level is 1 bar. Atmospheres, that's another really common one. This is very common for gas pressure in chemistry. There's also millimeters of mercury, and this is related to the height of a column on a mercury barometer. And then torr, named for an Italian scientist, and 1 torr is equal to 1 millimeter of mercury. And so here is a little thing that equates all of these together, including, right, this here, that 0 Celsius is 273 Kelvin, right? And so the other thing that I should have added on here, which is on your periodic table packet, it is a constant, but at standard temperature and pressure, which is 0 Celsius and 1 atmosphere, all ideal gases occupy 22.4 liters of space, right? So 1 mole of gas occupies 22.4 liters, right, at standard temperature and pressure. So we'll remember that standard temperature and pressure, 0 Celsius and 1 atmosphere, that is standard temp and pressure. Okay, so we'll start out with some laws here. Boyle's law, basically that the volume of a gas is inversely proportional to the pressure at a constant temperature, or volume equals a constant times 1 over the pressure. That would be Boyle's law. The next law, Charles' law, is that the volume of a gas is directly proportional to the temperature at constant pressure, or that volume is equal to a constant times temperature, which basically means that as you heat up a gas, the volume is going to increase. All right, just like Charles' law, the one we saw a moment ago, if you put pressure on a gas, the volume is going to decrease. And then, of course, the last one we have here, Avogadro's hypothesis, and that is that the volume of a gas is directly proportional to the number of moles at constant temperature and pressure, or the volume is equal to a constant times the number of moles. So basically, if you have more of a gas, the volume is going to increase. And so all of these get combined together into what we call the ideal gas law, which is a combination of the individual gas laws and can be used to predict the properties of gases under a variety of conditions. So here we are. This is the standard form that you will see it in, PV equals nRT, or PivNert. And in this equation, V stands for volume, usually in liters, pressure, or P stands for pressure, usually in atmospheres, N is the number of moles in moles, temperature in Kelvin, right? Notice Kelvin. It is in Kelvin, not Celsius. And the ideal gas constant, which has various forms that we will see on the next slide. And we use one form when we have liters, atmospheres, moles, and Kelvin. There's the one you will see most often. There are some others there as well. And the reason that we use Kelvin here instead of Celsius, hopefully you will understand this even before I say it, is that looking at the equation here, if we are working with Celsius and our temperature happens to be negative, right, that would mean at some point here when we are finished our calculation, we would calculate a negative pressure or a negative volume, and you cannot have negative pressures or negative volumes. That just is not possible. So keeping our temperature in Kelvin assures that our temperature is always a positive value, and so we always use temperature in Kelvin. Now, here we have 4 versions of the ideal gas constant, depending on what units we find ourselves working with. The most often seen one is this one with liter atmospheres per mole Kelvin. This one you will also come across in various situations with joules per mole Kelvin. I don't really see meters cubed pascals per mole Kelvin all that often, but you might come across it. And I don't know that I have ever worked with the one that is in liter torrs per mole Kelvin. That one I just don't really see ever. Okay, so an example of using the ideal gas equation, PV equals nRT. Okay, so what is the pressure of 7 moles of oxygen gas held in a 2-liter vessel at a temperature of 28 Celsius? So the first thing we're going to do is convert 28 Celsius to Kelvin, and we do that by adding 273 to 28. And when we do that, we get 301 Kelvin. The next thing we're going to do is rearrange this here to solve for pressure, which if we rearrange it, we get P equals nRT over V, and then we just plug in our numbers. Oops. Which would be N, 7 moles, R, which in this case we're using liters and atmospheres and all that, so 0.08206 liter atmospheres per mole Kelvin, times our temperature, which is 301 Kelvin, and then all of that over our 2 liters, right? Because we see in our equation here we've got 7 moles, 2 liters, and our temperature. And when we do all that math, if I could punch this into the calculator correctly, that would help. And we get a pressure of 86.45 atmospheres. Great. That's how that works. It's simple algebra, nothing more. Okay, then we get to the combined gas law, which we take PV equals nRT, we rearrange it to say PV over T equals nR, which R is a constant, and if we have the same number of moles that we begin and end with, we can find out the pressure, volume, and or temperature of any gas that we have the same number of moles in our beginning and ending state. So as long as we begin and end with the same number of moles, we can change the other conditions and see what the resulting pressure, volume, or temperature will be. And now it's time for an example using our P1 V1 over T1 equals P2 V2 over T2. right? And so we have a gas that has a pressure of 1.3 atmospheres in a closed 400 milliliter vessel, which, if you are following along at home, is 0.4 liters at 78 Celsius, which is 351 Kelvin. What will the pressure be if the temperature is lowered to 10 Celsius, which is 283 Kelvin? And so now we want to know what P2 is, right? So we are going to rearrange this. Now, one of the things you will notice after we rearrange this is that we have V1 and V2, but we're not changing the volume. So to make this easier, we just cancel those out, meaning that we have P1 T2 over T1 equals pressure 2. We put in some numbers, right? Our initial pressure, 1.3 atmospheres. Temperature 2, right? The temperature we are moving to, 283 Kelvin. Our initial temperature, 351 Kelvin. And we're going to get a new pressure, which, if we think about our laws, right, we're going from a higher pressure or a higher temperature, right? This is our starting, to a lower temperature ending. So we should have a lower volume, right? Because when you cool a gas, the pressure decreases. And when we do the math out, our new pressure should be 0 or 1.05 atmospheres. There we go. That is how we use the combined gas law. Then we have Dalton's law of partial pressures. So basically, Dalton's law of partial pressures says that the total pressure of a mixture of gases is equal to the sum of the pressures of the individual gases. Regardless of their identity, this will be true. So you mix gases, doesn't matter what they are, as long as they're not reacting, the pressure of the mixture will be equal to the sum of the individual pressures. Or pressure total equals pressure plus pressure plus pressure plus pressure, on and on. And we can also look at this. We can calculate our pressures based on our ideal gas equation, right? That a single pressure would be equal to the moles of that gas times the constant and temperature over volume. And so essentially we can say we add up all the number of moles, multiply by our things that are the same, and can get the total pressure, right? So just knowing the number of moles, the temperature, and the volume of the container that it is in, we can get the total pressure. And so one final example here, where we have 4 grams of hydrogen, 8 grams of nitrogen in a 5-liter flask at 25 Celsius, which happens to be 298 Kelvin. And so first off, we're going to figure out how many moles of hydrogen and nitrogen we have by saying 4 grams of hydrogen divided by 2 grams per mole of hydrogen, which is 2 moles of hydrogen, and 8 grams of nitrogen divided by 28 grams per mole of nitrogen, remembering that, right, hydrogen is H2, nitrogen is N2 when they're on their own. which would be, where's my, there we go, 0.29 moles. So then we can do just what we did with that equation. We can say 2 mole plus 0.29 mole times RT over V, or 0.08206 times 298 divided by 5 liters is going to give us our pressure. And when we do that, we get a pressure of 11.2 atmospheres. There we go. So that is an example using Dalton's law. Now, the last thing we'll talk about in this video is mole fractions. This is not really a super complex idea, but basically the partial pressure is equal to or directly proportional to the mole fraction, or the pressure fraction is equal to the mole fraction, or that we have our mole fraction here, which is equal to the moles of one thing divided by the moles of the total, right? Like any fraction. And that we can say that the pressure of the gas is equal to the mole fraction times the total pressure, right? Same here, mole fraction times total pressure will give us the individual pressure of that gas, right? So it's really just working backwards using Dalton's law, using some simple algebra. And so that is it. We will talk more about gases in a second video, and I will see you in class.